Hello, I am Craig Kibukamusoke of Structured Environment, a structural engineering consultancy based in the UK and Japan. Thank you for joining me on this webinar on the Eurocode design procedure on an extension project in the EC1 area of London that we have designed and analysed in Midas Gen. As we go through this webinar, I will touch on an overview of the project, the challenges we faced, how Eurocode was used, how we applied this all to our scheme, how I approached assembling the model, and the results in Midas. First, a brief overview of the project. Currently, in the UK, and in London in particular, house prices are extremely high. There are also many historic buildings in areas where planning laws make it difficult to demolish or alter. As a result, in recent times, there has been an increasing trend to extend or remodel existing buildings. Here are some examples of typical extensions. The picture here shows a row of houses that have all converted or extended into the loft. The style of loft conversion shown here is typically of timber frame construction. As well as extending upwards, basement extensions are another popular option. Here is a picture taken during the construction phase of a basement that we designed, and here is the finished furnished basement. However, due to the labour costs and the laws involved with underpinning shared walls in adjoining properties, construction costs are relatively higher than those associated with above-ground extensions. In this case, the property is a 5-storey masonry building with solid roof and floors. It was originally built in the 1600s as a warehouse or factory. This is an image of the building. In recent years, it has been converted into serviced apartments, which is when we believe the solid floors and roof were installed. The building is located in the City of London on a site between the legal and commercial districts of London. The property abuts a luxury hotel and neighbours an embassy and office buildings. With this background, the client in this case is a developer who has acquired the air rights above the existing historic property for development. The proposal is to build a 2-storey upward extension to the existing property, creating a penthouse maisonette. As the construction is due to begin shortly, we have prepared some superimposed images of the proposed structure as shown on the slides. As with any project, we faced some challenges. As London is a densely populated area, maximization of the livable floor space and flexibility of the internal arrangement was essential to ensure the client could obtain his desired profit margin. Here you can see some proposed architectural elevations. In order to obtain the planning permission from the local authority, an independent survey was produced displaying the impacts on the rights of life for the neighbouring buildings. This required each proposed level to be offset from the facade of the floor below and also put a height restriction on the proposed development. The finished floor to ceiling height affects the perceived comfort of the space, and this impacts the sell-on value of the development. So one of the main challenges we faced was keeping the depths of the structural members to a minimum and ensuring that their lighting rates to be installed without the use of heavy cranes. The design codes used in this project were the Eurocodes. As with most codes, Eurocode splits the actions or loads into 2 main categories: dead permanent loads and live variable loads. Dead loads are derived from the bulk density of the material, determining the volume of the material, typically represented in kilonewtons per meter squared as a uniformly distributed load. Live loads are displayed in a table within Eurocode. The values of the live loading are categorized depending on the proposed occupancy of the building. These two are commonly represented in kilonewtons per meter squared. In a Eurocode, horizontal loads such as wind loads are also classified as live loads. For example, a value of 0.6 kilonewtons per meter squared for a standard timber joist floor is usually adequate. However, for our project, we allowed for a higher spec floor, so we used loadings of 1 kilonewtons per meter squared. And typically, for a self-contained dwelling such as the proposed, a value of 1.5 kilonewtons per meter squared is adopted. For the scale and location of the EC1 project, dead loads, live loads, and wind loads were modelled on the structure. These loads are then applied to the structure and adequacy checks are then made. Ultimate limit state assesses the strength of the structure and ensures that the structure does not fail under ultimate forces and moments. For these checks, factors are applied to the loads. Service limit state assesses the serviceability of the structure and ensuring that the structure does not cause damage to the finishes, impair the occupation of the building, or create discomfort to the occupants. From our perspective, for a residential building, we aim to limit the deflection of the floors for comfort and limit the sway of the structure to prevent cracking to the fabrics. For the steel supporting internal timber floors, we allow for a maximum deflection limit of span divided by 270 as adequate. In addition to this, lateral sway in the steel moment frames, for example, is limited to height over 300. With this in mind, we began to develop our scheme. One of the requirements from the local authority was for the proposed window locations to follow those in the existing building. To ensure this and to create the proposed flexible 5th and 6th floor plans, we produced a structural scheme aimed to allow full-width openings in the south facade and frames that minimize weight. The proposed building is clad with a prefabricated wall and roof panel system. We therefore proposed a series of steel moment frames to be introduced at approximately 3.5 meter centers. This allowed the timber floor, wall and roof panel systems to be simply installed. In the longitudinal direction, braces were introduced in between bays of steel frames at both levels to carry the sway load. Apart from habitability, the limitation of the longitudinal sway was vital to ensure the structure does not load the abutting hotel. The steel moment frames were used to distribute the new loads onto the masonry perimeter wall without loading the existing solid roof, as the strength of the existing roof is difficult to verify. The steel frames were also designed to provide lateral stability when wind loads act on the structure. In plan, we designed a timber joist floor spanning between a series of closely spaced 203 by 203 universal columns as beams. These floor beams are then pin connected to the steel frame. The end bay towards the rear of the property was required to be of smaller 152 by 152 universal column steel sections to allow for enough space for the staircase to be extended upwards. Lateral sway in this bay is carried using 10 mm by 150 mm steel plate cross braces. In accordance with the conditions set by the local authority, we had to set back the 5th floor facade by 200 mm and the 6th floor by 510 mm from the existing brickwork. To achieve this setback and still keep the loads centrally over the perimeter wall, the ends of the main beams are cantilevered, and the effect of this created a staggered frame as shown. This is a detail of the cantilevering bearing pad. To assemble the model, we chose to build it in Midas by importing the AutoCAD file of the 5th floor plan and transposing plans to create other levels. Midas simply allows importing of AutoCAD data. I'm just going to demonstrate how we created the structure. So here you can see the imported plans with all of the internal steelwork as shown. Now to form the structure, we would highlight the plans. So here we have the 5th plan, the fifth floor, 6th floor, and roof. So we're going to transpose these plans and build the frames. So you just here we go. So I pick a point which is in the same position as the floor below. Oops. And then I've allowed for the height of each floor to be edited, and I click apply. So here the 6th floor is in place directly above the 5th floor, and I'll do the same again and move the roof plan. Okay, and to introduce the columns, we used a feature that Midas have called extrude. So using the extrude feature, you can set the section size you wish to use. So if we allow for our section size to be SC1, for example, if we allow for it to be SC1, we will then highlight the nodes we wish to be extruded to form the columns. So we'll highlight these ones on this east-facing facade at 6th floor level, which are forming parts of the columns. And then we would select the 2 nodes to create a plane that we want to extend them to. And then if we click apply, we should all create the columns for that wall. And then we would do the same again for the floors above. We just had to take a bit of care. We couldn't do them all as a group, as our shape actually it changes as it kicks out here to follow the existing plan of the existing structure below. And then we would then go in and draw in our cross braces and our diagonal braces, just so that we could get those in as well. Okay, so with using the Midas functions, we were able to simply build our structure using the data straight from AutoCAD. So once we had the model built in Midas, we began assigning properties and beam end releases and defining which connections are to be fixed or pinned, and assigning support points as shown in the screenshot. We then began applying the loads to the structure. The wall panel system was input into Midas as line loads and applied onto the perimeter beams. As shown in the screenshot, Midas' floor load function was used to model the timber floors and roof panels. This function allowed the floors to be distributed, and when applied to the structure, showed the span direction of the load. In this function, you can assign how much of the loading is dead or alive loads. In the story function, Midas automatically generates the story data and allowed us to input the relative level of each floor from ground level. The distribution of the wind load is dependent on whether the floor diaphragm is considered or not. For the purpose of modelling, we wanted to analyse the strength and lateral stiffness of the individual frames. So by selecting Do Not Consider under the Floor Diaphragm tab, in the analysis, the wind load is calculated and applied to each individual frame. However, obviously, in reality, as there will be a plywood floor, the diaphragm will allow for the wind load to be distributed between the frames. To represent this, select Consider under the Floor Diaphragm tab, and then a consolidated wind load is applied at the centre of the structure. The longitudinal wind load is taken axially by the beams and transferred into the brace elements. We use Midas Gen's built-in wind load generator to apply the wind load onto the structure. At this point, you can select to use the wind load code in accordance with the Eurocode. When calculating the wind load, the Eurocode allows for nationally dependent parameters to be input. So using wind maps, altitude, and geographical data, we determine the design wind speed. By inputting this information into the wind load generator and identifying the terrain roughness type, Midas will calculate the design wind load and apply it to the structure, referencing your story data. Before we can analyze the structure, we wanted to create a few load combinations. We used the steel automated combination generator in accordance with the Eurocode, with safety factors of 1.35 for dead loads and 1.5 for live loads. As defined within the guidance of the Eurocode, these factors used in the checks on the structure allow for a design life of 50 years for a dwelling. This generator references the Eurocode and applies the combination factors to reduce the design values when they add together, creating different load cases to be analysed on the structure. A particularly useful design tool is the envelope combination feature. An envelope combination automatically selects the worst case combination for strength and for serviceability. So this is our model. So I think, yeah, this is our model. And so one of the issues we found when we were assigning and applying the loads was we couldn't actually apply the loads, the floor load, using the floor load function. We found we had a bit of difficulty doing that. So one of the things we had to figure out and make sure we use. So this is a representation of the floor loads being applied, and as you can see, they are happening at every sort of beam and internal beam. So one of the issues we had was that we were unable to use this function without viewing the local axis of the beams. So let me see if I can pull that up. So we had to realign and ensure that the local axis of the beams were all in the right direction to allow the floor load function to compute. I think this was an error that occurred during the drawing phase within AutoCAD, and when it was then input into Midas picked up on the orientation and it threw up an error. So if we are then to run our results, I'll remove that. If we then to run our results and check the lateral displacement, okay. So, sorry, the lateral displacement. Here we can see on our legend that we've got a maximum displacement of 5.96 millimeters. with that, we are able to see exactly what our frames are doing. We can see the representation in terms of how the loads are applied at each frame and how much each frame is swaying. So you can see that the frames towards the middle of the property are experiencing greater amounts of deflection compared to those towards the south facade or those towards the north facade. So, for example, if we were to pull up the columns against the steel code check, let me close this. So the steel code check allows us to assess the sections and members with the applied loads against the load combinations in Eurocode. So it will show us how each member performs under the loads applied. So steel code check, here we are. So here it is saying the worst case member is the member 212. So if we put in 212, 212 is this member down here at 5th floor level. So we're going to pull up a basic graphic calculation sheet, and it will show that this member 212, and here are some of the properties of this member, the section size it is, and its effective length. It goes on to pull out some of the forces applied to the member under this load combination 12. So we can always check that back. Load combination 12 is our ultimate limit state combination. So we have that, and it shows all of the forces applied onto the column, and then checks it for bending, axial slenderness, and also for lateral sway. And here you can see we've got L over 300, so our story height over 300, and our actual lateral sway, which is well within the limit that we've allowed. So in addition to lateral sway, we'd like to also check vertical deflection, sorry. So in vertical deflection, we can see that the largest amount of deflection is actually found towards the center of the property. Now, here, when we were designing this, we had to use the function of the member assignment function, and this ensures that we can select the effective length of each beam so when we design it, even though we've said, you know, this beam is pinned here, fixed, within the design phase, it will, if we select it within the member assignment function, we can then use this entire effective length of this beam. So if I just pull up the member assignment function, try and find a particular member. So here we are. And this beam, if we then run the steel code check for just that beam, so we've selected that beam and run the steel code check for that beam, it says it's okay, we run the graphic check. So it's going to say the effective length is, the unbraced length is, where is it? 4.7 meters, and it shows again the loads applied to it, and it's referencing which load combination each time. So say load combination 1 is the worst case load for this beam, and it goes through, checks the bending resistance, actual resistance, and deflection checks. So here, because it's an internal beam and it's supporting a timber floor, it's span divided by 270, and along the length of the beam, that is less than the deflection limit. However, the deflection limit here represents, we found it represents a compound deflection limit. So if you've got a deflection limit of -1 at this location, for example, and along the beam it's -5, you're gonna, it's gonna show a deflection limit in the middle of -6, for example. So that's why that is displayed as that in this instance. Another good property that we found very useful, another good function, was the results ratio. So we can, let me unselect that. So we're going to highlight all of the floor beams and run the steel code check one more time. So we're analyzing all of them now and view the results ratio, and I think we should be able to just see a graph of all of the beams. So with this, it's checking each beam against the steel code with reference to the section size we've used, and it's showing the suitability for each beam for the loads applied against the section size. So here you can see beam 182 is heavily loaded, for example, and the bending moment of the beam in comparison to the allowable bending moment on the section size. However, here you've got a few beams that are a bit lower. So in the most economical way, we could have reduced the section sizes for perhaps anything under a ratio of 0.2 and provided them with a lighter section. But for our design, our site was actually in quite confined space, so we needed to ensure that the steels could be delivered onto site quickly and installed very quickly to allow us to get the structure up without causing hassle to the neighboring properties. But it was a very useful function, because however, if we did have one steel that was out, a ratio of 0.8, for example, and everything else was a lot lower, perhaps we could have changed the section size for that, for that one beam, or for the rest of the other beams, because they didn't need to be of that particular size. And the other function we used for this structure was the steel optimal design. Okay, so the steel optimal design was used to allow us to introduce a form of iteration. Here it's finally popped up, and it basically compares. It gives you a grade of each section as a ratio out of 1. So the closer the ratio is, which is the COM value, the closer that value is to 1, the more economical the section size. So here you can select the section size and it will come up and flag up and say the section size is no good, or it can say it's good. However, if you iterate and give them some dimension limitations, it can then iterate and find the perfect size for your design. But you have to then go back and check that it still works against for your design. So we could have had all of these as different sizes, but then for ease of installation, you'd have various connection details that don't match, different depths, different weights, that would look a bit off. So, you know, we could use this. We did use this to help maintain our structures and find sizes that worked within our depth. So for a lot of our beams, we wanted to keep them to a minimum depth of 200 mil to maximize the floor to ceiling heights within the house, within the penthouse. So we used this function for that. And finally, we wanted to check that the reactions onto the perimeter wall were kept to a minimum, at least evenly spread as possible. So we used the steel. We use this this function, and it basically shows us, if we remove that, this shows us our results, our reactions onto the perimeter wall. And here you can see we have a reaction of 152 kilonewtons. That seems to be our largest reaction. Whereas, and typically, as you expect, the end bays tend to be of lighter, smaller reactions. So everywhere else seems to be around the sort of 100 mark, except for these two. So we had 3 cases of bearing pad designs when we wanted to actually support this back onto the perimeter wall. And so we had the heavier ones that are probably 140 plus. So it would be this one, and this one. They were slightly more robust. And then we had these ones where we didn't have to we have to spread the load as much onto the masonry. And then we had the very light ones, which are on the corner as well. So they had to be slightly differently shaped. So this function was used to just maintain we're getting an even spread of the load around, and we kept tweaking our design to make sure that, you know, we weren't ending up with a 200 here and a 50 here and 50 here, when we could probably work the scheme and alter the internal beams to spread the load in a certain manner to get an even distribution. Okay, that will be all from me. Thank you very much for joining me on this webinar, and I hope if you have any questions, please contact Midas, and I'm sure they'll be able to help you. I hope you've enjoyed this. Thank you very much. Bye.